So my talk's going to be a little bit different than your general show and tell. So this is a DNA molecule. We've known about the structure for about 50 years now, but only recently have we begun to realize the technological implications of this molecule. To a large extent, the 20th century marked the turning point in human history where we saw the greatest acceleration of technology, science, and innovation. Everything from transportation to communication, medicine, electronics, and computation progressed rapidly. And it changed the way the world we knew it worked. So a primary driving force behind the 20th century innovation was the development of information technologies, specifically universal languages. In electronics, this was binary code. That comprised of 2 digits, 0 and 1. And it bridged the gap between mathematics and logic. Along with the development of the universal code was the development of electronics and machines that could, read and interpret this code. As it turns out, DNA was actually the very first information technology. It existed long before life existed, and that's over 1 billion years ago. It's a universal code comprising of 4 elements, A, T, G, and C, and the machinery capable of deciphering this code can be seen manifested in anything that is or will be living. Much like binary code catalyzed the transformation in electronics and innovation in that field, our hope is that the understanding of DNA could lead to similar breakthroughs in manipulating biological systems. So the pace at which we're moving in this, in these disruptive fields, many like synthetic biology that we're, learning as we go, is astounding. To put it in perspective, halfway through 2000, President Clinton and the Human Genome Project announced the first working draft of a human genome sequence. It was a tremendous milestone, but the cost of sequencing that genome was roughly around $3 billion. I mean, you can go and build the Empire State Building for that amount of money. Since then, we've had some exciting adventures and advances in sequencing that have specifically lowered the cost by 1 million-fold since 2004. So that's 5-fold faster than Moore's Law, which predicated the silicon-mediated technology of the last century. So with this reduced sequencing cost, we have a bunch of new and interesting technologies. For one, if we go back to considering DNA as an information technology, as a universal language, what's really stopping us from using it to store as a storage technology for our everyday needs and all this data that we're collecting now? Well, my PI thought just that, and he published a paper in Science last year basically documenting a protocol that allowed DNA to act as an information medium. So to put things in perspective again, 1 gram of DNA could hold over 700 terabytes of information, or 14,000 Blu-ray discs, which are like 50 gigabytes each. So in 1 gram of DNA that is thermostable, will last forever, and would fit on the tip of your pinky. So we're already seeing some of the profound technological implications of this molecule. And for example, Oxford Nanopore actually released a compact USB drive-like concept that would pretty much be targeted at consumers, less than $1,000, and you could do sequencing at your desk. But more important than any of these innovations is the fact that sequencing costs have made sequencing something that's commercializable and available to consumers. The potential to democratize that technology is there, and sooner or later it's going to become a reality that people are going to have personalized genome sequences. The problem being we have an information explosion. So you heard a lot about sequencing a genome, and then now you don't hear too much about it. You hear about 23andMe and stuff, but what happened to all the breakthroughs that would come about when we have the full human genome? Well, the problem is we have way too much information. Now think about the World Wide Web when it first started. We had this entire semantic information matrix, but we didn't have the tools to make sense of that information or impact our daily lives. So the next big thing is going to be to develop bioinformatic tools to really make sense of these personal genomes and come up with information that's relevant to our daily lives. So even though the cost of sequencing has rapidly fallen, a lot remains unclear about what we can do with that information. So right now, the current state of the next big project and where all the funding is going is mapping the human brain. So we went from mapping the human genome to mapping the human brain, and the Brain Initiative is backed by DARPA, NIH, NSF, and they're investing over $100 million this year in making these enabling technologies come about. But there's something in between that we've kind of missed out on, and that's the human phenome. We need to create a system that can also measure all the different characteristics of our phenotypes, behavioral traits, as well as environmental factors that are playing a big role in our daily lives. So we have the entire hereditary and genetic information of an organism, and we're soon going to have the entire neural network that that codes for our brains and helps us think the way we are. But in between, we need something to really take those two data sets and make meaningful impacts on our lives. And that's going to be creating a system to collect information in our daily lives. So my side project is called omics.io. We're trying to map the human phenome, and our goal is to create tools that will closely measure behavioral and environmental traits. So eventually we want to take a systems biology approach and map these to neural, cellular, and genomic pathways. So overall, we're interested in genomes, phenomes, exomes, metabolomes, all the biomarkers you're talking about. Those all are huge data sets that can be unraveled, but we need systems and platforms to really make sense of that data. So we're really interested in some sensor technology, both health and environmental biosensors, and that's where the whole self-tracking comes in. We're also trying to build a bunch of analytics, modeling, visualization tools. Privacy is a key component that a lot of people are missing out on. It's something that really needs to be built into these tools and these platforms. And our approach to biomedicine is more preventive care, predictive, and personalized medicine. So what we're building right now is a plug-and-play database and platform where you can go and use your Fitbit, your iPhone apps, and all the other sensors that are on the market, systems and platforms like 23andMe to get your genome sequenced. So you gather all this biometric data into one cohesive platform. And our hope is to really make more sense of these data, because these data points are fragmented about different devices, platforms, and as great as these tools are and these devices are, the problem becomes how much can an individual really invest in a different ecosystem for each biometric. So a big thing is going to be getting all these data points into a cohesive system. And the great part about Fitbit and everything is that they've provided a great API and documentation that allow us to really pull out the data from their different biosensors. So software is still under development. We have a working system that can pull in APIs from Fitbit, Withings, scales, and whatnot. And really, we're creating algorithms to really make sense of that data and to provide more actionable feedback. Right now we have these systems. So we decide we're going to go self-track, and then we start using the device or platform, and it provides data visualization, and you buy into the ecosystem. But we have to go back and make sense of that data. What does that mean to my day-to-day life? So a big part of our software is going to be doing that for the user. A lot of us had a reason to join Quantified Self, but for the majority of people, the big thing that's impeding their joining Quantified Self or doing all kinds of tracking is the fact that it's going to take a lot of effort and that currently it's too fragmented. With regards to some hardware development we're trying to create a Google Glass-like device to do some, it's all open source, and it's going to basically do some EKG, EEG monitoring. Technologies that don't currently exist on the market that are, wearables that people would wear to be continuously monitored. So essentially, we are targeting consumer devices. We're trying to build standards for health informatics, working closely with healthcare professionals, NIH, and physicians to really create standards that can really predicate, how this platform and other open platforms are going to grow. And a couple applications of our system right now include sleep disorders and Parkinson's. So we're just getting started. This is a little different than your typical show and tell, but we really want to hear from a lot of you guys who are doing quantified self, what issues you currently face with self-tracking, and what would help make the process effortless. The ultimate goal is to get as many people involved as possible. So I'd like to acknowledge my PI and mentor, George Church, at Harvard Med School, the Weiss Institute for funding a lot of my research over the last couple of years, everyone at the Personal Genome Project working really closely with us to integrate their open source platforms and allowing us to build tools for them, as well as Rensselaer Center for Open Source Software, which funds a lot of the open source work I do, and everyone here at Quantified Self, Josh, and everyone who's helped make this happen and allow me to present today. So, thanks.
Thank you. Time for just one or two questions.
Cool.
Okay, great, thanks.
Question. Have
Yep.
you run into TickTrack? And if you have, how does that differ from what you're doing?
So I haven't looked into it too much, but basically we're pulling in a lot of APIs, but the platform is essentially open source. The difference will be each user will be able to implement, plug and play any device that they have. I think the main difference will be the kind of visualization tools and algorithms we develop. So it'll ultimately be based on the work we do, but a lot of it's going to be open source. So we hope the community will also invest a lot into the system once it's up and running. But yep.
One more quick question.
Yeah,
So
no
right
problem.
Now, you're really concerned about the data bus and the data storage, and the visualization will come a bit later.
We're focused on both issues. Visualization is going to be how we reach out to customers and our end users, because it isn't as much creating cool visualizations as it is creating visualizations and presenting the data in a way that's meaningful. So whether that's us creating algorithms to make sense of this data for a person, basing it off their metrics, giving them an actionable feedback, but it could also be creating visuals that help them make informed decisions. So that's the whole purpose of the project as a whole. So it'd be great to hear from any of you guys who are interested in testing the product or getting involved in using it. Thank you.